Okay, so last week we started to do model theory, which is the study of structures over signatures. So after signature, the signature determines our language, and our logical language, and it also determines the notion of structure. And last week in particular, we looked at various notions of morphism between structures. So maps between structures. And since we're studying logic, one class of maps is the most important, and those are the maps that preserve logical properties, properties defined by logical formulas. And these were called the elementary embeddings. So the notion of elementary embedding is going to be fundamental today. So just to make sure we're on the main page, I'll just quickly go over it again using very slightly different notation, just for the sake of having variation. So let's recall an elementary embedding theta from one structure curly m to another structure curly m prime is a function theta on the underlying sets such that, and then we had this condition that last week was formulated. The condition basically says it preserves logical properties expressed by formulas. The condition was last week formulated by having any environment and composing the environment with an environment mapping variables and composing the environment with the function theta. Another equivalent way of thinking about this is that we're preserving logical formulas in parameters. I've explained what the notion of in parameters means a few lectures ago, but anyway, we'll see now. So we want to preserve every logical formula in parameters. So that means such that for every formula over our signature, the formula might be phi. I don't remember last week when formulas phi or oh, good, because I tend to, I'm writing a paper at the moment, but actually the deadline is tomorrow, so if I'm not completely switched on, it's because of that. But the syntax for formulas in the paper is phi, so it's phi and psi with the Greek letters, so I may kind of occasionally come up with Greek letters here. Anyway, so for any formula A with some free variables, x1 to xk, so remember this is our notation for we have at least these we have at most these three variables in the formula, and rather than interpreting the environment, we can interpret with parameters a1 up to ak from the structure M. If A holds in M for these parameters, for A1 to AK, then A also holds in M prime. Only, of course, these parameters don't make sense in M prime, but we can get parameters that do by using the mapping theta, which is, of course, what we do. So here we have theta A1, so in parameters theta A1 to theta AK. And that's the notion of elementary embedding. Remember from last week, because logical formulas are closed under negation, the other implication also follows. We also last week had the notions of homomorphism and embedding. These are weaker notions of, these are more general notions, more inclusive notions of morphism. So in particular, any elementary embedding is automatically an embedding, as the name suggests. Elementary embedding. If you've got an elementary embedding, it implies you've got an embedding. And if you've got an embedding, it implies you've got a homomorphism. And we also noticed that an isomorphism, namely a homomorphism that's an isomorphism of homomorphisms, so a homomorphism that has that's a bijection and its inverse function is also a homomorphism. We noticed, we also remarked that any isomorphism is an elementary embedding. The isomorphisms preserve logical properties. Yeah, and that's basically it for the definition of the notion. And we had a couple of variations that maybe I rushed over at the end. So mathematically, it's not really important. An elementary embedding, it's an embedding, so the function's injective. Mathematically, it's really irrelevant whether or not that injection is a subset embedding or not. If it's not a subset embedding, you can always rename the elements so that it is a subset embedding. But traditionally subsets have been an important part of set theory, and it's certainly, it's nice to have a structure and wonder if you can, like we did last week with the elementary substructure theorem, if you can cut it down to a smaller structure, but nonetheless the inclusion is an embedding. So for this reason, we introduce special terminology for those embeddings for which the function is a subset inclusion. So, if we have a subset inclusion from M to M prime, but not only do we require a subset inclusion, but we require that that subset inclusion preserves the function, the interpretation of function symbols, and preserves, we require it to be a homomorphism. Such a thing is called a substructure. So this is maybe what I didn't quite clarify last week. This notation, a subset notation between structures, means a substructure. So M is a substructure. That means literally what I just said before. The underlying sets, one is a subset of the other, but moreover, the inclusion is a homomorphism. That's what being a substructure means. We also have a notion of there's an embedded substructure in which that inclusion is embedding. Anyway, it doesn't, some people might distinguish, sometimes you want one notion, sometimes you want the other. It doesn't really matter because we're always going to, from now on, want to preserve the formulas. So as long as it's a homomorphism, that this makes sense, then M is an elementary substructure of M prime if the inclusion is an element. Let me just write it like this: an elementary embedding. And last week we had the elementary substructure theorem, or the countable elementary substructure theorem, that said if we have an infinite structure, we can always cut it down to a countable substructure. Moreover, we can do so in such a way that we include any identified countable subset of the of the larger structure that we want to include in the smaller structure, as long as the signature is countable. So we can always cut structures down. That's what we learned last week. Today we're going to go in the opposite direction, and we're going to see that we can always expand structures rather than cutting them down. So just to have the terminology for that, exactly in this situation when the inclusion is an elementary embedding, we say M is an elementary substructure of M prime. The converse terminology is we say that M prime is an elementary extension of M. And the notation for these two equivalent concepts is this kind of symbol, backslash prek ik in LaTeX. I think. So this says M is an elementary substructure of M prime. Okay, and as I said last week, we learned we can always cut structures down. So actually the main theorem today, which is not very difficult to prove, is the opposite, that we can always expand structures. So let's give the theorem straight away. Once again, in order to be able to expand a structure, it's important that the structure is infinite, because if you've got a finite structure, you can completely characterize the structure, including its cardinality, by a logical formula, because it's easy to find a logical formula that tells you exactly what the cardinality of the structure is. I mean, we basically did that in the first lecture on quantifier elimination. So the theorem that we're going to have as the main theorem today, like what I call the countable elementary substructure theorem, this is not a theorem that you will find in exactly this form with this name in logic textbooks, but I'll state the theorem we're going to have, and then I'll talk a little bit about what the associated results you'll find in logical textbooks are. So the theorem I like, and the one we're going to prove, is what I call the proper elementary extension theorem. This says that if we have an infinite, so I said we can't expand a finite structure, but we can't make a larger structure to elementarily embed it in. But if we have an infinite structure, we always can. So the theorem says if M is an infinite structure, then it has a proper elementary extension So this is what it means for M prime to be an elementary extension of M. We have an inclusion, subset inclusion that's homomorphism of structures, and the inclusion is an elementary embedding. Can you guess what it means for this inclusion to be proper?
Maybe M prime has bigger cardinality.
That will imply that it's proper, but that's not a necessary condition for it to be proper.
It's not equal.
Yeah, it's simply that it's not equal. So there's simply some element here that's not in the image of the there's not in the subset. So M prime is a proper elementary extension if the underlying set of M Well, I like to use this notation for proper subset because I like to use the equals for subset equals and this so this means a proper subset. Clarify your own notation in your notes if you use other notation to that, because some people use this just for general subset. Anyway, it's exactly that. There's an element here that's not in this subset, and then the notation I'm going to use for that is n. So again, we'll just drop the equals from here, i.e. So the inclusion function is not surjective. Furthermore, if both m and the signature are countable, then m prime can be chosen to be countable. We can find a countable such m prime. Okay. So let's, because this is the main theorem, let's put a box around it. So before going on, let me tell you what this is related to that you find in logic textbooks. You find similar theorems, but not exactly the same in logic textbooks. So the most closely related result that's somehow it's very, very close in spirit to this is last week we had the Löwenheim-Skolem theorem in its original form, which said if you have a consistent, a satisfiable theory and a countable signature, then it has a countable, and it has an infinite model, then it has a countably infinite model. We had then the modern version of that that's called the downward Löwenheim-Skolem theorem, which says if you have a structure, an infinite structure, then for any smaller cardinality than that, for any smaller infinite cardinality than that structure, you can cut the structure down to an elementary substructure that has that smaller infinite cardinality. And the upwards theorem says, conversely, if you have an infinite structure, you can blow that substructure up to, you can expand it to any larger cardinality. So CF, I always mean to look this up and I always forget. I mean, this is the standard abbreviation in English, presumably via Latin, for compare. So I'm saying compare this to the, so what I mean to look up is what it actually stands for. I know it means compare. I already wrote Löwenheim-Skolem's name last week, so I don't need to do it again, just the upwards LS theorem. So this theorem says if M is an infinite structure, then for any kappa, that's a cardinality, let's for any cardinality kappa as the maximum of the cardinality of M and the cardinality of the signature. Just like that. There exists an elementary extension of M that has cardinality kappa. There exists an M prime with the cardinality of M prime equals kappa. Of course, I mean the cardinality of the underlying set like this, but let's just write it for the structure. And M prime is an elementary extension of M. Okay. The proof of this is not actually much more, I mean, as long as one's got the axiom of choice, the proof of this is not actually much more difficult than what we're going to do today, but basically the same idea works. So you can think about that if you want. I mean, I don't really want to dwell on this because understanding the notion of cardinality in general is not a prerequisite for the current course. So this theorem looks more general, but it's not quite more general than this for one reason. So as this theorem is stated, this theorem, the statement of this theorem does not directly imply this. Can anyone see what's missing? That you normally see in logic books. So it's the combination of the countable part with the properness. So this does guarantee there's a proper elementary extension because you just take a strictly larger cardinality and the embedding is then necessarily a strict inclusion. But in the case, as you say, in the case that you have a countable structure and a countable signature, the theorem as stated here does not guarantee that there's a countable proper elementary extension. So that's the only way in which this theorem is kind of more powerful than that. I mean, mind you, everybody knows that one can strengthen this easily in this way, so it's not a big deal. But anyway, I like this statement because it focuses on proper elementary extensions, and it really, as I say, this is the main theorem of the lecture. The proof will take us like 5 or 10 minutes when we get around to it. But actually, what most of the lecture is going to be about is how one can exploit this theorem to do interesting things. So we're going to focus today actually on applications more of this theorem. And there are lots of applications and they've been pushed to get some very powerful results in mathematics. So we're only going to scratch the surface. And I'm going to give you like a little idea of how this theorem can lead to some nice applications. And the basic buzzword for the kind of methods that are connected with applications of this theorem is called nonstandard methods. So we're going to focus on the proper elementary extension theorem, the proper elementary extension theorem, that every structure expands to a proper elementary extension, opens up the possibility well, opens up the area, if you like. It's a gateway to the area of what are called non-standard methods in mathematics.
This isn't the Robinson sense.
Right, so very good. So the most famous area in which non-standard methods are used is a field called non-standard analysis, which was the brainchild of Abraham Robinson, who you were mentioning. So a magician called Robinson came up with this. So this includes. So what we're going to do at the end today is I'm just going to show you the beginnings of how non-standard analysis works. So this is due to Robinson. That's the most famous of the non-standard areas of mathematics. But we're going to start with some non-standard combinatorics instead, which is a much less famous area. The reason it's less famous is that traditional combinatorics is it's just using finite methods of finite mathematics. It's kind of a lot less frightening in some sense than analysis. So maybe people don't really need to have non-standard methods for it. And also the results are not really so impressive by non-standard methods. Whereas in non-standard analysis, this area really has been developed very substantially and has been used to prove new results in analysis. And it's still a very major area. I mean, it goes back, Robinson's development here goes back to the 1960s, but it's still a very, very active and major area nowadays. Right, so what I want to do is what I've been planning to do was to give an application, so do some non-standard combinatorics, then prove the theorem, and then do the non-standard analysis. But actually, seeing the time, which is 4:45, I've realized that the non-standard combinatorics will kind of, we'll get started, but we won't get to the end but by the break. And the theorem would actually just fit in the next 15 minutes, proof of the theorem. So let's actually do things in a different order. Let's prove the proper elementary extension theorem. And then, the good thing about that is if you're a theory person and you're not interested in applications, then you can just leave earlier, because the rest of the lecture is going to be applications afterwards. And the proof is really quite straightforward. Jump ahead in my notes with all the combinatorics in the middle. Right, so we'll start off with an infinite structure, which hopefully we were required to have, be an infinite structure for the signature L. And the basic idea is we'll expand the signature so that L contains constants for all the elements of M, and then we'll consider the logical theory that axiomatizes all the properties of M. Okay, so So we'll expand L by adding a constant, which I call, so to avoid too heavy notation, I'm going to call the constant symbol underline D for every element D belonging to the structure M. Okay? And we'll call the expanded language the expanded signature. So this means the expanded signature here. Call this L of M, the language of the structure M. And we simply consider the theory in the language Lm of the structure M. So we interpret, so obviously the structure is a structure for the language L, but we interpret the constants in the obvious way, and we consider the theory. So using the obvious interpretation of the new constants in curly M, consider the theory of the structure M prime of M, sorry, in the signature, in the expanded signature L of M. So if I was being really pedantic, or if I was using a proof checker, in which case I would have to be pedantic, we wouldn't really be calling this structure M, because the structure M is a structure for the original signature L, and actually the structure we're using here is really the structure expanded with interpretations of the new constants. But anyway, for the sake of an informal exposition on the board, let's not worry too much about that. It's easy to be more precise if one wants to put a bit of additional notation into it, which I don't. Now we're going to extend this further. We're going to add yet a new constant, and the role of this new constant is that we're going to extend the theory further, and we're going to have a new constant that we're going to force to be different from all the constants we already have. And then interpreting that theory, we're going to be forced to get a structure that has a new element in it. So extend the signature again by adding one more constant, which it's traditional to call infinity. So, and then we have a new signature which we'll call Lm prime. So that's Lm with the additional constant infinity. And we now consider the set of sentences. Consider the set of sentences in L prime of M called S, and that's defined to be, we have the theory of M in the language in the signature L of M with the original constants but not the infinity, and we add to that just a set of sentences saying D is not equal to infinity for every element D of the original structure M. Okay? And I claim that S is satisfiable. Can anyone see why S is satisfiable while I'm clearing the board? Something to think about. Did last week. So, yeah, very good. Because if we consider a finite subset of S, well, then it's the subset of the theory of M, together with only finitely many of these axioms. So we're saying that infinity is different from some finite number of the elements of M. But we can certainly satisfy that because we can satisfy that with the structure M itself, because the structure M itself certainly satisfies everything here. And if we've only got finitely many of these, well, the structure is infinite. So we've certainly got some element that's different from the finite collection of these. So by the compactness theorem, S is satisfiable. So it has a model. That's what being satisfiable means. So that, well, we've used M and M prime. So let's go to curly N for a structure N. N be a model of S. And now there's an obvious function from M to N, which is, consider the function that goes from the, so theta, that goes from the underlying set of the original structure curly N to the underlying set of the structure curly N, which simply maps D to the interpretation in N of the constant symbol representing the element D. Okay. And this is an elementary embedding. Then theta is an elementary embedding. So maybe, I mean, it's kind of obvious because S satisfies the theory of M, but let's just check that. Consider any phi in x1 to xk in the original language and d1 to dk in M. Suppose that, A, the formula. So suppose that A holds the d1 to dk in M. Well, that means in our M expanded with the constant symbols for d1 to dk. So this implies that in M expanded with the constant symbols, which we were again calling M, as I said, this was to avoid too much notation. So because the constant symbols were interpreted as the elements, that holds. Then this is this is now a sentence here in the theory of M, And because n models the theory of m, then n, and this sentence also holds in n, so because n models the theory of m. And this exactly says that n models a of theta d1 to theta dk, because here we've got the interpretation of these constant symbols in n, and that's how we define theta. Okay. It's an elementary embedding. We find the theta, or not quite finally, theta is proper because it's obvious that infinity is mapped to something that's not in the inclusion of theta. Theta is proper. So actually, I realize, I mean, it doesn't really matter, but I defined proper elementary extension, proper elementary extension earlier. A proper elementary embedding is the same thing. It's an elementary embedding in which the function itself is not surjective. So theta is proper because infinity in n is outside the image of theta. Elementary embedding. The only thing is, this is not any elementary extension, because the way we've constructed the way we've constructed n, you know, we just found some structure. It does not need to be a superset, does not need to be an extension of the original structure. There's no reason that this is an inclusion function. How do we address this? Elementary extension, how do we turn it into an elementary expansion? So we've got a proper elementary embedding. How do we turn the codomain into an elementary extension? That's what I mean. Simply by renaming. So let's not bother to write it down, but we just find an isomorphic set that you know, we know what elements to map the D's to because they need to stay the same, and then you kind of rename everything else. And that's easy to do if you have. Probably don't even need the action of choice for it, but anyway, it's certainly an easy exercise. So then, turn n into a proper elementary extension by renaming its elements. Okay. We're almost done, but we're not completely done. So I've rubbed the theorem off the board. What haven't I done? Get to the theorem at the end, which was the countability condition. Okay. So maybe, given that by my watch it's 2 minutes past 5, let's have a break. Well, can anyone tell me how we address the countability? Okay, so let's have a break. We'll start at 17 minutes past, and you can have 15 minutes to think about whether you can see how we make sure that n is countable in the case that the signature and the original structure are both countable. Okay, so it remains to fill in the last corner case of the proof here, which was what we're going to do with in the case that the model is countable. So I asked you the question to think about, in the case that the starting structure is countable, how do we make sure we get a countable n? I thought I would look in my notes to see what I'd written on that before, and I found that I actually omitted that from the notes when I wrote it. But anyway, I mean, you know, I know what to say. But did anyone solve the puzzle? So how do we make sure we get a countable n here in the case that we start off with a countable m and we started off with a countable signature.
Is this guaranteed by the proof of the compactness theorem somehow?
The compactness theorem?
Maybe I don't have.
Oh.
I don't have a concrete suggestion, but
It's-
a hunch down the Löwenheim-Skolem theorem that we proved. In the
Right,
previous
okay.
lecture.
Okay, so both these are good suggestions. So the proof of the compactness theorem used the proof of the completeness theorem. So it's guaranteed by the proof of the completeness theorem. But I mean, it is by the proof of the compactness theorem because we were using the compactness theorem. So yes. But more simply, it is literally just which used this same proof idea, it is literally just the original Löwenheim-Skolem theorem that we had last week. So if we have a countable theory if we have a theory in a countable signature that is satisfiable, then it has a countable model. So it's simply that. Our original signature is countable, the original model was countable, so therefore our extended signature is also countable, because we just added countably many new elements. So in the case n is countable, then n can be taken to be countable by the original Löwenheim-Skolem theorem. Okay, so we're done. Right, so as I said, then this is the theory of the lecture. We're going to do two different applications to look at how somehow the idea is really to look at how these proper elementary extensions work and how they relate to the original model. And this is the basis, as I said, of non-standard methods in mathematics. So the first area I'm going to look at is non-standard combinatorics. The application here is not very stunning, but the proofs are nice. And so what I like about it is we see a couple of nice proofs on the one hand. And the other thing is that I think it's a very good introduction to this area because it will help us understand how to think about these non-standard elementary, these proper elementary extensions. So what we're going to prove is our application is going to be a very famous result called Ramsey's theorem. Now there's a general version of Ramsey's theorem which exactly the same methods work for. I could do that, but just to keep it simple, I'm going to do a special case, which is still a case of interest, which is Ramsey's theorem for pairs. Ramsey's theorem for pairs. It's a very interesting theorem historically, by the way. Frank Ramsey proved this theorem in a very early paper on mathematical logic in the 1920s, but because he had an application of it to some very esoteric logical application that has not withstood, that people aren't typically, as far as I know, very interested in anymore. So for him, this was like a lemma to prove this logical theorem that he was really interested in. So the lemma has kind of, the theorem itself has fallen by the wayside, his original reason for proving it. But this lemma he proved, which is now Ramsey's theorem, is is a very important result theorem in combinatorics and has been the source of a huge amount of follow-on work in the 100 years since Ramsey's original paper. Yeah, Ramsey was a very brilliant person who worked in many areas of mathematics and economics and other things, and sadly died very young. So in his 20s.
Excuse me, can I ask a detail? Is it with an E or an A?
So this is an E.
This is an E, yeah, because
Yeah.
I think I remember another Ramsey with an A.
At least I hope it's with an E.
Okay.
Anyway, Ramsey's theorem for pairs. Hands up if you know Ramsey's theorem. I mean, if you've done, okay. If you've done a course on discrete mathematics, I mean, at some level you eventually get to Ramsey's theorem. So the version for pairs is this, which is for any k greater than or equal to 1, there exists an n greater than or equal to 1, such that every graph, again, we're going to look at simple graphs, so the ones that have no little loops and which are no self-loops on vertices, and in which the edges are reflexive. Sorry, not reflective, that's what I've just said. They don't have loops, the edge relation is symmetric. So such that every graph with at least n vertices or a k anti-clique. I mean, we know what graphs are because you must have done courses on it, but also we did k-coloring of graphs in an earlier lecture, so we've already done graphs. A k-clique is a set of k vertices such that every two distinct vertices in the set have an edge between them. So it kind of, like a 5-clique looks like this. K anti-clique, it's also called a k independent set sometimes, is the opposite. So it's a set of k vertices that there are no edges between any of them. Okay. And apart from being very important in combinatorics, this is of interest for numerical reasons as well. I mean, it's actually quite a nice little exercise to prove that if k equals 3, and this implies n equals 6, as far as I remember. So you can quite easily prove this bit for yourself. If you've got at least 6 vertices, then you must have a triangle or an anti-triangle. K equals 4 implies n equals, I've actually forgotten, but something like around 17, but I don't remember exactly what the 18 or something, maybe somebody knows. And the reason I'm writing these numbers down is because so this is the smallest such n, and here it's an open question what, even for the case k equals 5, it's an open question what the smallest n is. We know that one exists, and that some bounds on it are known, some quite good bounds now. Open question what the smallest n is.
For 4, that's 18.
18, okay, right, thank you. That was close. And this one's up sort of somewhere up in the high 40s.
43 to 46.
Right, okay, the mid 40s. Doesn't really matter. I mean, we're not going to address the actual numbers here. We're going to do logic. So that's Ramsey's theorem for pairs. So we're going to prove this using using non-standard methods. Although really, it's not quite right to say we're going to prove this itself by using non-standard methods. What we're really going to prove using non-standard methods is a variant of this result called the infinite Ramsey theorem. So many people knew this Ramsey's theorem. This is for pairs because we're talking about cliques and anti-cliques in a graph. The more general theorem is to do with colorings of the graph and to do with sets that are monochromatic, so have the same color in the graph, and sets that might have more than two. So here we're looking at edges, it's colorings of a set. And anyway, it doesn't matter what the more general version is. The fact that this is a property about graphs is the reason it's the Ramsey theorem for pairs, because we're looking at pairs of elements and whether there's an edge or not. That's why it's called the Ramsey theorem for pairs. So many of you had heard of Ramsey's theorem and knew Ramsey's theorem. How many of you have heard of the infinite Ramsey theorem? Because I don't know if that's something you do in discrete maths, because often discrete maths is about just finite graphs and structures. But the infinite Ramsey theorem is nice because the numbers go away.
Excuse me. This is what we will prove a stronger version than this. So does the thing we're going to prove imply this, but it also implies more, or is it equivalent?
We'll see.
Okay.
We are going to prove this, but we're going to use the non-standard methods to prove the infinite theorem, and then we are indeed going to get that the infinite theorem implies this. But the proof of that is not immediately direct. But we'll do that first, actually, and then we'll be left with the infinite Ramsey theorem. So the infinite Ramsey theorem, so for reasons I don't understand, in English, when you qualify, you put something like the English in, the infinite, it wouldn't be right to say the infinite Ramsey's theorem. That doesn't sound right. So we need to take the possessive off, and if anyone can explain that to me, not actually now during the lecture, but afterwards. The problem with being a native speaker in a language is that one just knows the grammar by instinct rather than really why that's the case. So I don't understand why it's wrong, if it's Ramsey's there. But anyway, the infinite Ramsey theorem simply says that in any infinite graph, there is either an infinite clique or an infinite anti-clique. And I should also say the use of the word either here is linguistically wrong because there could be both. But still, and maybe that I shouldn't have included that. But anyway, it's too late. I've put it there. So for every infinite graph, let's not say either in this case, every infinite graph has at least one of an infinite clique or an infinite anti-clique. Okay, that's the infinite Ramsey theorem. So this is what we're going to prove using non-standard methods, and this is the result that has a difficult proof. I mean, more difficult than. In a sense, the difficulty in proving this theorem is here, is in proving the infinite version. And then it's nice that the finite version follows. And actually, just to get it out of the way, while they're both on the board, I want to start by giving the argument that the infinite Ramsey theorem implies the finite Ramsey theorem. Okay. So let's do that. Proof of infinite Ramsey theorem implies, I call this the Ramsey theorem for pairs, but we'll call it the finite Ramsey theorem. Right, so let me just take stock because I just want to see. Okay, we can fit this on this bottom bit of the board here. So we want to prove the finite Ramsey theorem. So let k be greater than or equal to 1, let that be arbitrary. And we're going to again consider the signature for graphs, which just had the one binary relation symbol. So over the signature for graphs from an earlier lecture, we've just got the one binary edge relation symbol. Consider the theory. Well, let's just say consider the set of sentences. But as before, we're going to have the sentence that says there are no self loops. So the edge relation is irreflexive. We're going to have the sentence that says, so there's a space here between the two sentences. We can just put a conjunction. It's saying both these things. So we're going to have the sentence that says that the edge relation is symmetric. And we're going to have the two sentences that say there is no k clique and there is no k anti-clique. So we've started the proof here, we've got some k, so we let k greater than or equal to 1 be given. We want to carry on with the proof here. So we want a sentence that says there is no k clique, so we can say that by it's not true that there exists x1 to xk such that x1 to xk is a clique, so that means the conjunction over I from 1 to k and over j strictly greater than k and less than equal to I. So this could be a less than here. Strict less than. Okay, so if this conjunction is true, x1 to xk form a clique. This double conjunction, so it's not true that there exists some elements that form a clique. And similarly, it's not true that there exists some elements that form an anti-clique. So it's not true that there exists x1 to xk such that same conjunction, if we consider any k strictly less than j less than equal to I. Oh, hang on. A strictly less than j less than equal to k, right? For loops where we count I from 1 to k and we count from 1 to the number below k and we count j from the number from I plus 1 up to k itself. Sorry to get the details, simple details wrong, but there we go. And in this case, we want that there's not an edge between xi and xj. Only this formula does not quite say that there is no anti-clique. Looks like it should, but there is something missing. Can anyone see what's missing? Put the missing thing in here, so let's add the move that. So.
They're different.
Yeah, they need to be different because we didn't need to say that. We didn't need to say the x1 to xk were different in this case because we don't have self loops. So because of the irreflexivity, they're forced to be different in this case. But when we're saying there is no edge, there's nothing to force the xi and xj to be different. So here we need to say xi is different from xj. And anyway, there is no clique and there is no anti-clique. So this is the set of sentences S. So the models of S are graphs with no k-clique and no k-anti-clique. So by the infinite Ramsey theorem, S has no infinite models. By the infinite Ramsey theorem, S has no infinite models. And we had a result last week that if a set of sentences has arbitrarily large finite models, then it has an infinite model. So this has no infinite model, so therefore it does not have arbitrarily large finite models. So this was the first application of compactness last week. So by last week, IRT has, S does not have arbitrarily large finite models. But what this says is that there exists some n such that for structures of size n upwards, S is never a model. So there exists an n such that all structures of size greater than or equal to n are not models of S. And if they're not models of S, well, that means if they're graphs, so if they satisfy the first axiom here, then they're not a model of S, then, well, they must fail one of these two properties. So either they have a clique, or they have a k-clique, or they have a k-anti-clique. So any such structure that is a graph necessarily has done with proving that the finite theorem follows from the infinite theorem. And that I think is a very nice argument. And it's a bit like what we did, it's quite similar to the application we had, which was again an application of, essentially this is an application of compactness. It was a bit similar to the application we had for this Erdos, this De Bruijn-Erdos theorem in the previous lecture. Again, sort of talking about relating properties of finite graphs and properties of infinite graphs. Yes?
Why did we check that xi is not equal to xj if j is greater than I? And xi is equal to xj if the indexes are.
Well, of course. Here we're just saying, this is just saying it's not true that there exists k elements. We're just seeing what this first order sentence says. So this first order sentence says it's not true that there exist elements x1 to xk satisfying these two conjunctions, and if we don't tell the x1 to xk to be different, then of course they can be different. Then of course they can be the same. Yeah, it's just because the logical formula needs to say everything. Right, so now we've proved the finite theorem, assuming the infinite theorem. So what remains to be done is to prove the infinite theorem, and for that we're going to use the non-standard methods. Okay, so now So this takes a bit longer. But this is where, hopefully, via this result, even if the mathematical application is not stunning, because one can perfectly well, it's not that hard at all to prove the finite Ramsey theorem just from scratch, as most people that have seen it before, can give a pretty short proof of it. But as I said, the main idea here is to get our heads around the idea of how these non-standard extensions work. Anyway, so now we're going to have the proof of the infinite Ramsey theorem. So let's start off with an infinite graph. So it has a set of vertices and a set of edges. But we're going to view it in any case as a model of this sentence saying that a structure is a graph. Okay, so it's a structure. So it's a first order structure. It's a structure in the sense of this course, where this is where V is the underlying set, and E is the interpretation of the edge predicate, the edge relation predicate. So since it's infinite, viewing it as a structure, by the proper elementary extension theorem, it has a proper elementary extension. So by the proper elementary extension theorem, G has a proper elementary extension G prime, say, so let's just emphasize that that's an elementary. So this is just the order symbol, the prec eq written in the other direction, emphasizing it's an elementary extension of G and it's proper. So we can say G prime is some V prime E prime, where because it's an elementary extension, V prime is a superset of V, and then E prime is a relation, is the edge relation on V prime. Again, because it's a proper elementary extension, whenever we consider E prime between two vertices that come from G, then it will coincide with E. Okay, because it's an embedding. The embedding, the inclusion from G to G prime is an embedding. So because it's a proper elementary extension, there's some element in V prime that's not in V. So let's choose one, and as is standard, we'll call it infinity. So choose some infinity that's in the elementary extension, but not in the original graph we started with. And what we're going to do is we're going to perform an iterated construction of two disjoint sets, subsets of the original graph G. And it's iterated that we're going to number them with natural numbers in stages. We're going to grow the two sets such that one of the subsets is always a clique and the other one is always an anti-clique. So we perform an iterative, counting through the natural numbers, that means construction of sets Cn An, natural numbers n, such that if we take the union of Cn and the disjoint, but take the union of the two they have n elements between them. So each each time we're going to add exactly one element. Cn is a clique in G. An is an anti-clique. We're trying to construct either an infinite clique or an anti-clique. So we're going to grow these two sets, and then at the end, the union of the C's or the union of the A's will be the required infinite clique or anti-clique, depending which one grows infinitely often. But so that things work, we're going to maintain a further property, two further properties, which we require that for all vertices in Cn, it holds that in the extended graph, V is connected to the new node in the new vertex infinity. So this is in G prime. I mean, don't really need to say that because we've got E prime here, but anyway. And the anti-clique, we require that the elements of the anti-clique are not connected to infinity in G prime. So let's draw a picture. We have our original graph G, and we've expanded it to a larger graph G prime. And this expanded graph has vertex infinity that's not in the original graph. And we've got, for example, some C and some A that we're constructing in stages in this way. I should say, that we're growing them as well. And C is a clique. So, for example, if we've got 4 elements in it, might have some other elements, but we got 4 elements in it. They also, it's a clique, but also more than that, all the vertices in here are connected in the larger graph to infinity. And A is an anti-clique. None of those vertices are connected to infinity. So we simply construct these as follows. So C and A and constructed as follows. At 0, we of course take the empty set. And then, in order to construct Cn and An for n greater than 0, so let's maybe, so for n greater than 0, we note that in G prime, we have that it holds in G prime that there exists an X such that for all the finitely many in C at the previous stage, there is an edge in G prime from X to V. But of course, the E prime is the interpretation of the syntactic edge predicate in the structure G prime. Here I'm talking about a formula, so I'm just I'm not writing E prime because I'm using the syntactic predicate E, and I'm interpreting it in the structure E, in the structure G prime. So there exists an X such that it's connected to every element of C n minus 1, and it's not connected to any element of A n minus 1. This is these two properties here. So it's not true that E X B.
Excuse me, at this point we're just conflating like the elements V, vertices and symbols for vertices, right? And on fly.
Right, so yeah, so here this is a finite conjunction and a finite conjunction taking elements from the structure. So I'm writing this, but I'm using those elements as parameters in the formula. Okay, so this is the same notation I was using at the start of the lecture, including parameters in the we have a formula with 3 variables and I'm including parameters in here. Okay, and the reason
these are variables. The V's are variables or constants?
No, neither. They're parameters. Elements of the structure, and if you want, this could be a formula with some 3 variables here, and we have an environment interpreting those variables as the elements of the. But I'm just using the notation for parameters that I had earlier, and the reason for writing the property of being an elementary embedding earlier in that way was because I'm now going to use applications like this. So by the property of being an elementary embedding, here this is a formula in parameters all taken from the original structure G, and therefore since elementary embeddings as well as preserving first order properties reflect them, this property, if this property holds in G prime, it also holds in G. Why does this property hold in G prime? Because it holds for the element x equals infinity. So we're using that element to guide, essentially, we've expanded our structure, we find this element infinity, we use the properties of that element to guide our search for the clique and the anti-clique. That's kind of the idea of how this works. So we have that in G, the same formula holds. So that's, and what that means is there exists some element of X that is related to all the elements of Cn minus 1 and is not related to any of the elements of A n minus 1. Okay? Can anyone see what we do now? We check to see whether, so this element, so let W be an element of G satisfying this, witnessing this existential statement, witnessing the above formula, the above exists X. And now we check to see whether W is related to infinity, has an edge to infinity in the graph G prime. So if the W is an element of G, and if in the case that there's an edge from W to infinity in G prime, then of course we include W in C, because we need to maintain that property that all the elements of C have all the elements of C have edges to infinity. And if there is no edge to infinity, then we include the W in A. So if this, we define C of n to be equal to Cn union W, with an plus 1, an to be equal to an minus 1. We leave that unchanged. Else, we define we leave Cn unchanged. So this should be minus 1 there. And we define an to be equal to an minus 1 together with W. And clearly we maintain, and this clearly maintains the properties. So we're nearly done. So we define finally C to be the unions of the union of all the CNs. And it's a directed union because they're growing. With A to be the union of the ANs. And because of we're adding one element each time, at least one of these unions is infinite. So at least one of C and A is infinite, possibly both. And by construction, if it's C, it's an infinite clique, and if it's A, it's an infinite anti-clique. So by construction, anyway, C is a clique, whether or not it's infinite, and A is an anti-clique. At least one of them is infinite, so any infinite graph which we started with, the infinite graph we started with, has either an infinite clique or an infinite anti-clique. Okay, well, perfect length of theorem as it turns out for the time. So it's exactly 6 o'clock, so we'll start again at 1/4 past. Are there any questions? Okay, good. 15-minute break. Okay, so for the last hour, we're going to do the second application of the proper elementary extension theorem. So this is already said what it's about. This is what's called nonstandard analysis. So I'm not going to write the history, but it's worth saying just a little bit about the history of where these ideas came from. So you all know mathematical analysis, hopefully, and you know that a lot of the ideas about derivatives and integrals go back to Newton and Leibniz. And when they were developing their approach, Newton and Leibniz justified the notion of what a derivative is using a concept called an infinitesimal. So it's like an infinitely small number. So you could say, in order to calculate the derivative, we look at the curve at the current point and for an infinitely small distance away from the current point, and we use that infinitely small distance to calculate the slope, and we call that the derivative. And of course, this idea of an infinitely small distance, known as an infinitesimal, a number that's infinitely small, is a bit problematic to reconcile with other properties of real numbers. For example, you can, if a number is not equal to 0, you can take the reciprocal. You can take 1 divided by the number, And what happens if you take 1 divided by an infinitely small number? Well, you get some infinity or something. But anyway, there are many issues with what it means for a number to be infinitely small. And of course, now we axiomatize the real numbers, and by the axioms for the real numbers, there cannot be infinitely small numbers in the real numbers. So, yeah, mathematicians and philosophers were puzzled for ages how to make sense of calculus without infinitesimals, and that or how to make sense of infinitesimals did not seem to make sense. So you need to make sense of analysis without infinitesimals, and eventually, especially in the 19th century, this led to the development of the now rigorous school of analysis based on limits, and this what people often call the epsilon delta formulation of concepts such as continuity and derivative and this sort of thing. And so mathematical analysis, as it was taught today, finally came into its own, and one does it without any use of infinitesimals. However, the arguments using infinitesimals are often kind of more convenient in some sense. You can do quick heuristic arguments involving infinitesimals, where if you do things rigorously using epsilons and deltas, you have to realize that you need 3 epsilon here and epsilon over 2 somewhere else, and this kind of thing. And these sorts of numerical complications arise. But anyway, it was thought that the 19th century had established the correct way of doing analysis. It should be done without infinitesimals, using limits and epsilon delta arguments and this kind of thing. So it was something of a revolutionary idea I think in the 1950s, the logician Abraham Robinson realized that actually mathematical logic could be used to bring infinitesimals back to life, so to speak, and to establish a rigorous foundation for the kind of arguments that the early developers of analysis were using. And this field is the field called nonstandard analysis. So this is due to Abraham Robinson, and was developed, I think, from the 1950s onwards. And as I already said earlier, it's still a very active area today, and it's had some actually quite some quite influential developments have come from this area, and it's even solved some questions in mathematics. But we're going to just do the very basics of how what the basic idea is, and how the proper elementary extension theorem leads to such a rigorous development of an analysis involving infinitesimals, infinitely small real numbers. So the basic idea from our point of view, but it's not always presented in this way, and I'll discuss a bit how it's normally presented in a moment. And the basic idea is we consider the real numbers as a first order structure. As a structure. So what are we going to throw in? Well, we'll have the set of real numbers. We'll certainly have the addition and multiplication and their units, as always. Well, from that we can define the order, but let's put it in explicitly. But we're not going to. We want to do some analysis and stuff. So at the moment we've still got a decidable theory, as I said in one of the introductory lectures, by the theorem of Tarski. But we'll allow ourselves to throw in other things like, for example, function symbols for interesting functions from analysis, exponentiation, sine, cosine, this kind of stuff. So we're at leisure, meaning free to do as we wish, to add functions and relation symbols. And I guess the idea is rather obvious now, given what the subject of the lecture has been. It's simply, we simply consider a proper elementary extension of this. So consider some proper elementary extension as is guaranteed to exist by the proper elementary extension theorem. Of course, in this case, it can't be countable because we're starting off with an uncountable structure, but it can still have the same cardinality as the real numbers. So this is typically called R star, so the extended real numbers. So of course, it's an elementary extension. There's a subset inclusion here. So 0 is still going to be 0. 1 is still going to be 1. But these operations now extended to act on R star. Of course, on actual real numbers, they behave just as they did before. But so we've got a plus star, a multiplication star, an order star, and so on. To show, first of all, so this has some new element in it, infinity, if you like. We were always calling it infinity. But we're going to show that this expanded structure contains infinitesimals. Okay. Before going on, so we just to say we've obtained this using the proper elementary extension theorem from the start of the lecture. But actually, in books on non-standard analysis, there's often a different approach is taken. Rather than a hammer of a theorem that gives you, that just expands the structure, they use an explicit construction of such an R star. So often, and this is based on a construction called the ultra power construction, which is a very nice model theoretic construction, which we're not going to include. We're not going to cover in this course, but just to say, often R star constructed using this is referred to in the literature as the hyperreals.
Excuse me, can I ask?
Yeah, please do.
I remember that these hyperreals have a relation to what ultra filters.
Yes, indeed.
This is a different thing than an ultra power.
An ultra power is a product quotiented by an ultra filter. So ultra filters are inherent in a very important part of this construction. This construction requires the Boolean prime ideal theorem, or whatever it's called, which is the theorem that tells us that sufficiently large ultra filters exist that allow us to make this construction. Anyway, one benefit of doing this is that this construction is kind of not really sensitive to the signature you start with, and it's just automatically the case that all functions on the reals have natural extensions to functions on the hyperreals constructed in this way. So that's the benefit of that approach. But anyway, we're not covering that, so we're simply going to show that a lot of what's important for non-standard analysis just follows from the mere fact of having a proper elementary extension. So we're going to begin with the proof that such a proper elementary extension contains infinitesimals. So star for us is going to be this arbitrary proper elementary extension, and we're going to have a proposition saying that infinitesimals exist. Proposition is that we're going to have two statements. So there exists an infinitesimal is the first one. But what is an infinitesimal? Well, it's an E in R star such that it's greater than 0. Now, because it's an element of R star, just to be very, I mean, people would normally write just greater than 0. Well, people would just normally extend the greater than relation to this structure and just use it without worrying too much. But I'm going to try to be careful just to put these stars on, because this is your first exposure to such things, just so that we know what structure and the relation to taking place in. So here we've got E is positive, and can anyone guess what the defining property of an infinitesimal is?
Smaller than positive numbers.
Yeah, so it's smaller than all the actual positive numbers from the reals. And so for all, let's keep it consistent with the notes. Yeah, for all epsilon greater than 0, we're not just to use standard sort of analysis like notation. Than all actual positive real numbers. A positive hyper number, if you like. So this says that E is an infinitesimal. I already said one of the issues with infinitesimals is that the troubled people is that if you've got an infinitesimal, well, what is its reciprocal? Well, its reciprocal looks like it should be something infinite, and indeed it is. But never mind, it just turns out this structure has infinite elements. So the second property is there also there exists an infinity in the extended reals, which is infinite, meaning for all x belonging to the actual reals, it holds that x is less than, because infinities are. Oh, sorry, this should be a star here because we're involving the infinitesimal E, and here again, x is infinity is an extended real. This needs to be the star. So this says that infinity is an infinite number. Of course, it's positive because this condition implies it's positive. It's infinite. Now you could say, well, of course it's got to have an infinity because our very construction of a proper elementary extension, we threw in an infinity to begin with. But the infinity we threw in to begin with, their infinity just meant something different from the starting structure. The infinity we threw in to begin with need not be an infinity in this sense. It might end up anywhere. We don't know exactly where it's going to lie in the order theoretic structure on R star. So now when we use infinity, we're going to really mean an actual infinite element satisfying this property. Okay, so I want to prove this because it's going to be our an illustration of how one reasons with that.
Excuse me. I'm just curious, how would one translate this to a formula? I can translate all of this to a formula except the condition of the inclusion into the ordinary reals.
So these cannot be stated as formulas because here we're quantifying over actual real numbers.
Yes, yes.
So that cannot be stated as a formula.
It cannot be.
Yes.
Okay.
And it's really important that neither of these two properties can be stated by formulas, because this is an elementary embedding. So the same formulas are true here as are true here. And this is going to be important because it allows us to reason in this structure with infinitesimals and then bring the result back. It's called the transfer. There's a transfer theorem that says if we prove the first order property here, we can bring it back to the actual reals, which is where we're wanting to actually establish things. But of course, the existence of an infinitesimal is not a property we can bring back to the actual reals, and also the existence of an infinite number is not a property we can bring back to the actual reals. So yeah, so just as well, right? If we could express these with a first order formula, something would be wrong. So to prove this proposition, well, first we have we've got a proper R star is a proper extension. So of course R star contains some element not in R. But we don't know whereabouts it lies on the extended real line. It might not be infinite and it might not be close to zero. So we call such elements new elements. So because in the real numbers, the formula, so basically the typical thing we do to establish properties of R star is we establish properties of R and then transfer them to R star. And then we're going to work with R star and then we'll transfer them again back to the real numbers when appropriate. So we look at properties like this. We have that R proves that every number is either greater than or equal to 0 or less than or equal to 0. So R star proves the same property. So we know that. So let's call this new element. I don't seem to be giving it a name. Yeah, never mind. But because R star proves the same property, the new element is either positive or negative. Because the new element, so it's either greater than or equal to 0 or less than or equal to 0. Of course, it's not 0 because it's a new element. So the new number is either positive or negative. And if it's negative, its negation, which is also definable by a first order formula, is its negation is then a positive new number. So there exists a positive new number. Cases. There are three cases. So firstly, the positive new number is an infinitesimal. Okay, so then we found our e, our little e. In which case, how do we obtain an infinite element? Well, we take the reciprocal of the infinitesimal. So this is an infinitesimal e. So then e to the minus 1, this is to the minus 1 operation in the extended structure, is an infinite element. This e is not Euler's number. Okay. When you take the right e to the power of something, it looks like the usual exponential function. Never mind. This e is an infinite number. Let's just say it is infinite. If you didn't have to the minus 1 in your signature of functions, never mind, you have the first order formula for all x is not equal to 0. There exists a unique y such that x times y equals 1, and you use the validity of that in R star to get you the reciprocal. So the second case is that the positive new number is infinite. So let's call it infinity. And in that case, how do we get an infinitesimal? We do infinity to the minus 1. So then infinity to the minus 1 in the extended structure is an infinitesimal. Okay, so those are the two easy cases. The difficult case is, what do we do? So the third case is the positive new element D is neither infinite nor infinitesimal, and in which case, by the definitions of infinite and infinitesimal, it means it must be sandwiched between two actual real numbers. So satisfies sum A is less than star D is less than star B, or sum A, B in the reals, both positive. So in this case, we need to, from this information, we need to find in the structure R star, we need to find an infinitesimal. And this involves a very mildly ingenious idea, which is, anyway, it's a nice idea, which is we define L to be the supremum in the real numbers of those real numbers that are strictly less than D. Or less than equal is the same because D is a new number, so they can't ever be equal. So all actual real numbers, the supremum of all actual real numbers that are less than the number D. Such a supremum exists because the set is bounded above by B. So this is the supremum in the real numbers. Now, the structure R star itself does not have suprema, So this supremum need not, it's obviously the element L is obviously strictly greater than, hang on, what did I want to say about it? Yeah, it's obviously strictly greater than all the real numbers with this property, but we don't know whether it's less than D or greater than D. Okay. And R star can't have bounded suprema in general, because if it did, it would then become a complete ordered field, in which case it would be isomorphic to the real numbers, but it's not, because it's a proper elementary extension. So R star itself does not have suprema, but we're taking the supremum in the real numbers here. And what we do have is that then the absolute value of D minus L is an infinitesimal. Really minus star in the extended reals and absolute value star. Okay, but both can either be in the signature, the absolute value, or the minus, or otherwise they're again first order definable. So minus is just the inverse to addition, which was in the signature. Okay, and one can prove that that's an infinitesimal. Oh, and then once we've got the infinitesimal, then its reciprocal is infinite. Okay, so what I want to end with, so we know that infinitesimal numbers exist and infinite numbers exist. So what I want to end with is just one result which shows how concepts from analysis have nice formulations in this non-standard analysis setting using infinitesimals. And we'll start with basically one of the simplest concepts, and that's the notion of continuous function. And we'll start and we'll also finish with that, because I don't want to go any further than this, but it's to give you a feeling for the way this area works. So again, I'm going to call this a proposition. So suppose we have a function symbol f in the original structure. And again, as I said, if we were working with the actual hyperreals constructed as an ultra product, sorry, as an ultra power, which is a special case of an ultra product, if we were working with the hyperreals constructed as an ultra product, then we wouldn't need to worry about these function symbols, because all functions on the reals extend to functions on the hyperreal. So then we have the proposition that the following equivalent well, I'm assuming that f is a function symbol that represents the function f on the real number. So the first one is that f is a continuous function. And the second one is that f star enjoys a property that expresses continuity in a natural way. So the standard analysis for f being continuous is for all x, for all epsilon, there exists a delta such that, well, anyway, you know, so I don't need to recite it here. In the case of that we've got infinitesimals around, we have the nice statement that for all reals, hyperreals, is prove that f is continuous at some a in the real numbers. Okay, so continuous at a particular argument. If all extended reals, what we show is that if x is infinitesimally close to a, sorry, we'll say this is infinitesimal. Like that, we have the property of being infinitesimal, and this implies that the extended f applied to x minus, it's really minus star, but I'm not going to write star everything, minus f of a is also infinitesimal. So once again, this is not being expressed. This is not being expressed by a first order formula. This is a meta property about the structure. But nonetheless, it allows us to reason in a natural way about continuity. And the idea is simply to be continuous. Well, you know, the idea of continuity is you're continuous at A if you stay close to A, the function itself does not, the value of the function does not change very much. And we can make precise what it means to not change very much by staying close means staying really, really close, we're infinitesimally close to A, then the value of the function, well, this should be, oh, it doesn't matter if that's F star. The value of the function remains infinitesimally close to the value there.
To say f star in the second instance of f. I think
yes, we could.
Yeah,
absolutely. So the point is, the f star is an extension of f to the extended reals. So it's because A is an actual real, it's exactly the same thing. So in my notes, I don't have the f anywhere, but I don't have the star anywhere. Right. So as you saw, I was thinking. So I'm thinking because there's a nice proof here, and I kind of wanted to cover the proof. Tell you what, we'll do one direction. I can't do both directions in the time, and I obviously don't want to overrun because it's late enough as it is. Implies 2. No, but oh, okay. Oh, okay. Yeah, good. Who wants 2 implies 1? Sorry, so 1 implies 2 is outvoted by 2 implies 1. I'm not. I don't remember which is the more interesting direction actually. So I have to admit I haven't looked at this for 2 years. So let's prove 2 implies 1. Now, hopefully we can do this in. So suppose 2 holds. We want to prove. Oh yeah. Let's do 1 implies 2. Because 2 implies 1, we have to do we have to end up coming up with an epsilon delta argument. So whereas 1 implies 2, we can use that. Good. That was a good choice for those of you who voted for 1 implies 2. So suppose f is continuous, and suppose x minus a is infinitesimal. For some extended real x star. And now that this is infinitesimal. So to prove it's infinitesimal, we need to show it's positive. But that's obvious because it's got an absolute value. So we need to show it's less than every positive real. So to show that f star x, the absolute value of f of x, infinitesimal, consider any. We're not doing an epsilon delta argument, but I'm still calling it epsilon here. So consider any epsilon in our star, in the reals, 0 with epsilon in the real numbers. And we want to show, we need to show that the absolute value, well, there should have been an A here, is less than starred epsilon. Right. So by continuity, in the ordinary sense, there exists a delta such that greater than 0, such that for all y in the reals, but now the point is we can use an actual first order property now, so that the sentence for all y, y minus a is less than delta, implies fx minus in the real numbers. Where well, we've supposed that f is continuous at A, so that holds. So therefore, this is a first order property, and because the embedding is elementary, we have the same property holds in R star. It's the same. Okay.
For star? Or that should be y for
That should be a y. Okay. Indeed. Yeah, okay, so this holds because of the continuity of f at A. So the same formula, so this is just a formula in the signature. So now we don't use the star on f because it's because f is just a function symbol here. So the same formula is true in R star. But then that means this holds for all y in R star. So in particular, if we can now instantiate the universal quantifier with x. I should have used some other symbol like d or something rather than x, just to be clearer that this is not a variable, but x is an element. X is an element of R star. But anyway, so in particular, x minus a is less than delta implies, and now it's a meta level implies that f of x minus f of a is less than epsilon. But of course, the difference between x minus a is less than, sorry, that's the delta, is less than delta because delta is an actual real number, and f of x minus and x minus a is infinitesimal. that so this holds because x minus a is infinitesimal and delta is a real number with delta greater than 0. So therefore this holds. So this holds, which is what we wanted to show. What was needed. Sorry, so here we have the first order formula holding, we're instantiating that with a particular x, so now we're talking in the real world about the structure, so really I should put these stars back on here. Because we're now not talking about formulas, we're now talking about properties of the structure. So we're done, that's the proof of 1 implies 2. What I will do is I'll put the handwritten notes online, so those of you who are interested can see the proof of 2 implies 1. But of course, all we've done here is show that the notion of infinitesimal that one gets from a proper elementary extension allows one to characterize in a natural way an important mathematical property, namely the notion of continuity. That's all we've done, is not very much. To get an idea for how the whole subject of analysis can be developed along these lines, I'm going to put a link on the course web page to a textbook by Kiesler, a model theorist who's done a lot of non-standard analysis. And those of you who are interested can have a look at this textbook. And the idea of this textbook was to try and present analysis from first principles using infinitesimals as a pedagogical approach to giving a different foundation for the subject. Anyway, I think that's enough for today. Are there any questions?
So what are the elements of R star look like? Is this like complex numbers when you have like 1 plus 3e plus 7 infinity, or?
Well, so it's a linear order because we can prove in the reals that we've got a linear order. It's also an ordered field because we can prove as a first order property that the real numbers are an ordered field. So in that sense, it doesn't look like the complex numbers at all. It can be the cardinality can be the same as the cardinality of the reals. But apart from that, it's really hard to understand really what they look like. You can think about the ultra power construction if you're mentally able to do that. It's not very easy to think about.
I think the question was whether they can be represented somehow as linear combinations of some elements. If you take a real and then some.
Oh, I see. Right. Okay. Sorry, I misunderstood. So okay, there is a structure which is around every real number. You have the infinitesimal neighborhood, and there's the notion of a finite hyperreal, namely one that's not infinite, and every finite hyperreal is in the infinitesimal neighborhood of some actual real number, and that actual real number is uniquely determined. So the finite part is indeed like a disjoint union of such infinitesimal neighborhoods of actual real numbers. The infinite part is the reciprocal of such stuff. So that's as good a picture as I have. And it's not that I actually work in this area or anything. Right? So so sorry, I misunderstood the question. That's a good question. Yeah. Any other questions? Good, right. So yeah, we're going right down the wire today. See you next week.